why don't you just open the poster up and we'll just perhaps you can put it into context as to why you put the poster together in the first place,
Sure.
because you actually were one of the co-authors of this poster, weren't you?
Yes. So there's a challenge in antibody discovery and biologics, particularly around things like affinity maturation and lead optimization, where when you're looking at real-time binding interactions, you have the higher affinity the interaction, the slower the dissociation is, and basically the less observations you're measuring. As things dissociate very slowly, not a lot is happening. And that is a real challenge. And a lot of people perceive that there's strict limitations to the ranges that you can assess. And there's often a need for orthogonal confirmation. So this poster addresses two simple approaches, that don't require special reagents or anything, to really lower the limits of that sensitivity detection and really get accurate ranking and determinations of things that are in the high affinity regime.
Brilliant. So please talk us through it then.
Okay, so I'll start off with actually sort of a image that describes this problem.
Sure.
So if you look at the time to measuring just 5% dissociation
Yep.
and compare that to a KD values, you can see for things that are in this mid 10 to the minus 5 or faster range, it's easy. 20 minutes of dissociation is more than enough to get a really well constrained fit. But as you start to approach 10 to the minus 5, that's 1.4 hours to see only 5% dissociate. And if you go out to 10 to the minus 6, that's 14 hours of dissociation to see only 5% dissociation. So you can imagine if you had any sort of drift or artifacts in the system, those measurements would be almost impossible in a
Right.
real-time approach. So here we propose two solutions. One is using short and long dissociation phases. So this is a normal capture kinetics experiment where we used a capture select anti-human FC antibody on the chip surface to capture IgGs. We did 4 injections of just buffer with hour-long dissociation. Then we queue behind that 4 injections of antigen increasing concentration with only 5-minute dissociation. So this is a nice short bundle of injections. It doesn't take too long.
Right.
And then immediately after that, another injection of the highest concentration with an hour dissociation. So we're able to use this leading hour-long dissociation as a good reference across all of these injections. And, time-wise, they're not too far separated. So this experiment doesn't take longer to run than our standard approach, really, but we're able to collect an hour of dissociation data and really push the affinity estimate or the dissociation estimate down to about 1 times 10 to the minus 5, which is good to be able to do accurately in a full-scaled screening type run without taking a long time.
Right.
If you need to go even slower, there's another approach that we call chase kinetics, where this
Right.
is actually a, a, a single wizard run, but it is our standard capture kinetics experiment where we would do the loading of the array, then maybe 8 to 10 blanks of buffer. These are with 15-minute dissociations. Then we have our 5 concentration series, all at 15 minutes. Then I've done a second injection of the highest concentration of antigen. This is actually kind of optional, but it's good for confirming that you've achieved like an Rmax and you understand what your saturation of the surface is. Then 10 cycles of just buffer. So we're getting basically 4 hours of dissociation data collected. And then a final high concentration injection, which we call this the chase injection. So from this, we're able to see how much binding capacity did we gain here versus here. And that tells us how much has dissociated over this amount of time. And
Right.
you can do this. This is 10 injections, so 4 hours. You could do this for 14 hours or 24 hours if you want to, as long as you have stable or directly immobilized things. And that enables you to really push this dissociation measurement limits there. And we'll come back to how we do that. So if we look at this data in the standard approach,
Yep.
that's what's shown here in these. So these are 12 different antibodies immobilized in duplicates from 3 different surface ends. So they're actually getting smaller left to right, but it's hard to see because it's all scaled. Most of these are fine to be assessed for affinity. You can see we have 30 picomolar interactions that we're measuring at this 15-minute dissociation. But at the top, we have this one clone where they've all hit an off-rate limit, which for 15 minutes I set at 2.5 times 10 to the minus 5, which is a 2.2% dissociation in 15 minutes. So that's our limit for this sense of sensitivity for this. And then we have another clone that's obviously dancing right around that level because the two lowest densities also hit that limit. So we have a clone that's below that limit and a clone that's sort of at that limit in 15 minutes. If we scroll down to the hour-long dissociation data, you can see now we've recovered the ability to assess the off rate and affinities of basically everything, including that MAB1. It's hitting the limit at the lowest surface densities, which means again, its actual KD is probably right near that cusp of the setting that we've done, which in this case I put at 1 times 10 to the minus 5, which is a 3.5% dissociation within an hour. So we've been able to now, pretty accurately measure our off rates down to about that limit. If we
Right.
then consider this chase experiment, so from these first 5 injections, we've already determined our R max and our on rate, and now we have these long dissociation time period where we're just doing buffer blanks. We can take this report point value using zeroing the data of this chase injection at the end and just using this report point value and calculate a percent bound based on, the R max that we had from the kinetic fit earlier. And from that, we can actually calculate an off rate using this very simple equation where if we have the percent bound and the time that we've allowed the dissociation to occur in seconds, we actually get a KD value, which can then be applied to the kinetic estimate, in calculation of KD like this. And you can estimate for as long as you're willing to do these injections for. So, if it's 14 hours, 24 hours, and easily push that dissociation time measurement out to like, 10 to the minus 6 or potentially even lower.
Right.
And if we look at a comparison of these results from these experiments, you can
Yeah.
see we have the standard approach on the x-axis, the sensitive test on the y-axis, and so it's a scatter plot. In green, we have the hour dissociation. You can see we basically get the same exact numbers for everything except for the highest affinity clone where we've actually hit the limit at the 2.5 on the 15 minute, and now we can measure it at 1.5, 10 to the minus 5. For the slow. The chase approach actually gives us the same value for that one, which is good. We see slightly slower dissociations measured by the chase on some of the other ones. I think there's a little bit of kinetic heterogeneity in some of the fits that it kind of looks around. But interestingly, the estimate of off rate from the chase approach breaks down for clones that have more rapid dissociation. And that's, I guess, kind of obvious if you go back to the hour data and you say, if you look at something like this, this is an hour of dissociation. If you went out to 4 hours, there's nothing left to bind. So the chase approach is very good for looking at very high affinity interactions with very, very long dissociations. But if you have a range of dissociation rates or things that are dissociating more rapidly, something like the 60-minute approach or the standard approach are actually more appropriate because it's not sensitive out to or in these narrower ranges. I think 2 times 10 to the minus 4 was kind of a threshold for it in this experiment. Yeah, so that is these two approaches in a nutshell. Obviously, you can access this poster on our website. Oops, sorry. And I really appreciate you taking the time with me today, Rizwan, to talk about this.